All right, let's look at this problem. We want to use superposition to find the current Ix labeled here in the circuit. So what does that mean? We can find the contribution of to Ix by this 10-volt source by killing the 3 amp source. We can find the contribution of Ix due to the 3 amp source by killing the 10-volt source. But what about this dependent source? Can we kill a dependent source in superposition, or do we have to leave that in the circuit? We cannot kill a dependent source. That's key. An ideal voltage source, we say we kill that by making it a short circuit. It has 0 volts, but additionally, an ideal voltage source has an internal resistance of 0 ohms. So when we kill it, we get 0 ohms and we get a short circuit. An ideal current source has an internal resistance of infinite ohms. So when we kill it, an open circuit gives us infinite ohms. A dependent source, well, that depends on the rest of the circuit. We don't know what its equivalent resistance might be in order to kill it. So in superposition, we can kill independent voltage source, we can kill an independent current source, but we leave the dependent source intact. And it's in fact dependent upon Ix, the variable we're trying to find. So we'll create our two circuits, and what we're trying to say is that our Ix is equal to Ix prime, and that's the contribution due to the 10-volt source with the current source opened. So we can just draw it not there, or you can draw this little open circuit there if you choose. And then we have to, it's going to be that plus that contribution of Ix due to just the current source, where our 10-volt source, which was here, we've killed it by inserting a short circuit. So when we're trying to look at these two circuits, the first one where we just have the voltage source, well, that's fairly easy. It's just a single loop. So we can just do a single KVL around this loop. So our KVL equation, negative 10 volts plus our Ix times 2 ohms, Ix prime, times 2 ohms plus 1 ohm across these two resistors. And then we're going to the positive reference terminal plus our 2 Ix prime. That's all equal to 0. So what we want here is Ix prime. So if we solve for Ix prime, we get Ix prime is equal to 10 volts divided by 2 ohms plus 1 ohm, that's 3. This also has a unit of ohm in order to make it a volt. So that's, oops, divided by, lost our pen, divided by 5 ohms. That's an ohm. So that's equal to what? That's equal to 2 amps. So we can write that right in up here. This is equal to 2 amps. And then we can go solve for our Ix prime prime. So going to solve for our Ix prime prime, we use this lower circuit. And we see, well, here we have a node here. How will we solve for this? It's not just a single loop or a single node pair. If we use nodal analysis, this is labeled as V, so we can call that V prime prime. That's the voltage across the current source. This would be 2Ix prime prime, the voltage from this node to ground. And we could do this with a nodal analysis, where if we look here, let's write an equation first that tries to get we need a dependent source equation for Ix prime prime. So this current Ix prime prime, it's flowing in this direction, and this voltage from here to here, that's our V prime prime. So what we have is that our Ix prime prime is equal to the negative of V prime prime divided by 2 ohms. So there's our dependent source equation. Our nodal equation, we have V prime prime minus 0 over 2 ohms plus V prime prime minus 2Ix over 1 ohm is equal to the 3 amps flowing in, right? So we just have the one nodal equation. So when we simplify that, we get what we multiply through by 2. So that implies then that we'd end up with 3v prime prime 2 minus 2 times 2ix, so minus 4i, is it an x? Yeah, ix prime prime is equal to 6. And if we substitute in, that means if we substitute in for v prime prime is equal to negative 2ix prime prime, so we get negative 6ix prime prime minus 4ix prime prime is equal to 6. So our ix prime prime is negative 0.6 amps. So we just, went through our nodal analysis. We needed even though we only had one node, we second equation for the ix prime prime, which was the dependent source. So then we can put that in minus 0.6 amps, and that gives us an ix of 1.4 amps. So we see the contribution of ix due to the current source is negative, so that makes sense. The current source is flowing in the opposite direction. Due to the voltage source, it's positive in the direction of the defined ix. So that makes sense, but let's just go back up and check it on our circuit. We solved for ix is equal to 1.4 amps, so there's the 1.4 amps there. Then this current has got to be equal to the sum of ix plus 3, so that's going to be 3 plus 1, 4.4 amps, and our ix was 1.4, so that's 2.8 volts. So instead of going back and trying to solve for V, because we did that, let's solve on the outside loop. Our outside loop in our check, so our check, we'll do it up here at the top. We get negative 10 volts plus 2 times 1.4 amps, 2 times 1.4 plus 1 times 4.4 plus 2.8 is equal to 0, and that's 0.4, right? So we get 2.8 plus 2.8, that's 5.6, plus 4.4, we get negative 10 plus 10 equals 0. Check. So we should do a check on that. And again, noting that what we found out here about this current ix is that the contribution due to the current source is in the opposite direction of the contribution due to the voltage source. And that's an interesting thing to always find out. The contribution, and we could also look here and say, well, this current of 4.4 amps, that's flowing in this direction, right? It's positive. So this dependent source is absorbing power. But both of our independent sources are supplying power. So we can also do a power check. Key thing to remember in this problem is that when we kill the sources, we kill the voltage source by shorting it, that was down here. We kill a current source by opening it, that was right here. In both of these circuits, we cannot kill the dependent source, so we left those intact. The dependent source was dependent upon ix, and ix changed in both of these circuits.